often do we throw items to save time and energy? Probably more often than we think. Whether it be trash, a high shelf, or our laundry, it saves a little more time in our day. Now think about if we could create robots that could precisely throw any object into their respective location. The title of the paper we decided to read is TossingBot, Learning to Throw Arbitrary Objects with Residual Physics. The TossingBot system enables a robot arm to place objects rapidly into boxes located outside its maximum kinetic range. The TossingBot formulation uses trial and error to learn to grasp and throw from visual observations while learning throws that compensate for the dynamics of arbitrary objects. The goal is to investigate the relationship between grasping and throwing.
Take a step back and think about throwing for a second. While it's easy to take for granted as a rather straightforward motion, there is literally a select group of people that make millions of dollars a year for their particular skill set in throwing. Add in other factors like unique object dynamics and environmental interference, and you start to realize that it's actually incredibly complex. It is this complexity that has long prevented robotics applications from integrating throwing motions into their standard functionality. This paper describes the process of a robotic arm developing adaptive throwing skills, and does so in the hypothetical context of extending the speed and range of a robotic arm in a warehouse-like sorting operation or a pick-and-place task. This development, however, could easily extend to assistive robotics, help further the robotic imitation of human movement, and even lead to new insights about different throwing processes through the use of neural networks. The team of researchers enabled the TossingBot to develop throwing skills by using a conceptual model called residual physics. This model starts with a prediction of the throwing trajectory velocity according to standard projectile motion, neglecting object dynamics and air resistance. A residual velocity, which acts to adjust the initial prediction, is then acquired over a training period by machine learning, which is carried out via a neural network. This network takes into consideration a wide variety of factors that can influence each throw, supervising the learning process of how to weigh each characteristic by observing which throws are successful and what factors contributed to this success. The robotic arm's grasp of each object, particularly its location and orientation, was a major factor focused on in the paper.
TossingBot consists of a neural network that takes as an input a visual observation of objects in a bin and the 3D position of a target landing location, and outputs a prediction of parameters for grasping and throwing. The learning objective is to optimize the prediction such that the executing grasping followed by the throwing results in an object landing at each time step. To compute the visual input, we capture RGBD images from a fixed mount camera, project the data onto a 3D point cloud, and orthographically back project upward in the gravity direction to construct a height map image representation with both color and height from bottom channels. Within the simulation, the task is to pick objects from a cluttered bin and stow them uniformly into the boxes such that all boxes have the same number of objects regardless of object type. The simulation helps robots learn successful gripping and throwing of both seen and unseen objects, which is later tested using a real robot arm with this learned information. The resulting system is able to grasp and throw arbitrary objects into boxes located outside its maximum reach range with an 85% throwing accuracy, and generalizes to new objects and target locations.
The project discussed in this paper involves an astounding number of different subject areas that would typically be considered specializations. In reading this paper, students will undoubtedly see the value of interdisciplinary work and be challenged to think critically about how they can seek out the benefits of integrating other disciplines into their own work, either in their own skill sets or through collaboration with team members. One of the more abstract but incredibly impressive findings of this paper was how very basic sensor data eventually led to intelligent object categorization, simply by optimizing a task for successful throwing. This hints at the immense potential of neural network usage for making discoveries that lie outside the assumptions of pre-prescribed human categories, similar to the way that babies and young children learn sophisticated classification skills from very basic interactions and simple data.